Okay, so let's learn about universal gravitation, gravity. Chances are you, if you're like most people, have some pretty serious misunderstandings about gravitation. Like a lot of people think it's something that's unique to Earth. It is not. Every single particle of matter in the universe exerts a gravitational force on every single other particle of matter in the universe. It's just the world's big, so we notice it. Another common misconception that people have is that gravity somehow uh, vanishes when you go into outer space. When you leave the atmosphere, it goes down significantly or goes away completely. And I've definitely heard NASA commentaries where they refer to the microgravity climate aboard the space shuttle, or here in the zero gravity environment of space. Believe it or not, if we had a mountain that was as tall as the orbital altitude of the International Space Station, and you stood on the top of that mountain and got on a set of scales, you would weigh almost what you weigh now. I mean, gravity's a little bit weaker there, but less than 1% weaker than what it is here. So there's plenty of gravity there. That's not why people float around the space shuttle. We'll get to that later. My point is, lots of people have misunderstandings about this. Let's clear this up. Okay, so first of all, let's start with this. Gravitation is the force of attraction between any two objects in the universe. Remember, it takes two objects to have a force. And there's this action at a distance force, which is really weird because Isaac Newton came up with this idea. And at the time, it was like suggesting witchcraft that somehow something could pull on something without touching it. But there are a few action at a distant forces, and gravity is one of them. And so it exists between any two objects. So I have object one is called the Earth. Object two is this rock. Sometimes we refer to these smaller objects as a test mass, and then this is the main mass. Usually, when we talk about gravitational interactions, there's usually a disparity in their masses, but it doesn't have to be. So anyway, I have this rock. It has a mass of 1 kilogram. I'll talk about the difference between mass and weight in a little bit. It has a mass of 1 kilogram, so it is pulled towards the center of the Earth with a force of 10 newtons. But remember, a force is something that exists between two objects, and Newton's third law tells us that both objects feel that force equally in opposite directions. That means, just as the world pulls down on the rock with 10 newtons of force, the rock pulls the Earth upwards towards its center with 10 newtons of force. The difference is 10 newtons of force on a 1 kilogram rock makes it accelerate at 10 meters per second squared. The Earth is way more massive, and so it accelerates a lot slower, and yet it does have to move. The thing is, I could take that same rock into outer space, far away from the Earth and anything else like that, just to make things more simple for us, and it would fall towards the astronaut, and the astronaut would fall towards it because there is definitely a gravitational attraction between this object and this object. Take any two objects in the universe of your choice, there is a gravitational force between them. Whether you notice it or not, it exists between all objects. So now I have a 1 kilogram rock that's now going to fall towards a 60 kilogram astronaut, and vice versa. And in this case, the astronaut is going to accelerate at 1/60th the rate of the rock because the difference in mass is not so extreme. But notice the force of gravity has gone down tremendously, as you would expect, because the total amount of mass involved is much smaller, so the gravitational force involved is much smaller. But make no mistake about it, they would fall together. If you took an ant and a piece of sand and set them in outer space, they would fall towards each other. No object is too small to have gravity, and no distance is too great to which gravity won't be exerted. Now, Isaac Newton, when he had his big aha moment with gravity, he realized that it's proportional to the product of the two masses involved. Okay, so you have to have two objects that each have to be made of matter and have mass, and that mass pulls on the other mass with a gravitational attraction. So let's just take two objects, M and M, and say the force between them is Fg. Okay. Now, if I double the mass of one of them, then the product m times 2m would still give me 2m squared. So that means the force is now twice of what it was before, because here it's just m squared. Now it's 2m squared. So I've doubled the force of gravity between them because I doubled one of them. Had I doubled this one instead, I would have ended up with the same result. It doesn't matter which object. Double the mass of the world, you'd be pulled towards it twice as much. Double your own mass by eating a lot of pizza, you're pulled to the world with the same amount of force, or double the amount of force. Now let's try changing both of them. I make this one half as much mass. I make this one 6 times as much mass. Well, 6 times 1/2 is 3. So I have 3m squared. So I have 3 times as much gravitational force as I had in my initial situation. It's simple, just the product of the two together. Isaac Newton also realized by looking at Kepler's laws of planetary motion that gravitation would also follow an inverse square law. So, in other words, the force of gravity is proportional to the inverse or the reciprocal of r squared. So take two objects. Now, by the way, this r is the distance between the centers of the object, not between their surfaces. And College Board likes to ask questions like that, where they have them touching each other and asking about the pull of gravity. It's center to center, the center of this object and the center of this object. That's what this r is. So we start off with r. If I double the distance between their centers to 2r, well, I have now 2 squared, so that would be 1/4. So I have 1/4 the gravitational attraction that I had when they were twice as close. If I moved a distance 3r away, well, now I have 1/3. So I have 1/3 squared. So I have 1/9 the gravitational attraction I had before. Now look at this beauty here. This was what Isaac Newton considered to be his greatest accomplishment, his law of universal gravitation. This was something he was super proud of. Right? Keep in mind, this guy, first of all, probably the smartest man who ever lived. The guy who invented physics. He invented physics. He invented calculus. I mean, but of all the things he came up with, this is the one he was most proud of. Okay, he called it the system of the world. And here's the idea: the force of gravity, which we're going to call F sub g, is equal to, I like to use a capital M and a little m. Sometimes we use just an M1 and an M2. I like to say, like, I have a big mass and a little mass, like the Earth and you. Okay, so I like this type of notation, but you could use M1, M2. The two masses of the two objects involved in the gravitational attraction. It's the product of their masses divided by the square of the distance between their centers. All right, but then we have to have this multiplier designated by a capital G. It's called the gravitational constant, or the universal gravitational constant. And we need to have this multiplier because we want the force to be expressed in newtons. We're measuring mass in kilograms, and we're measuring distance in meters. And the universe just didn't know that when it came up with the idea of gravity. And so we need something to multiply this by so that we can use kilograms and meters and get newtons. And so this had to be experimentally determined, which is a pretty cool thing. Like, someone had to do this. I'll talk about that in a second. But once it was determined what it is, the number they came up with was 6.67 times 10 to the negative 11. That's a vanishingly small number. Gravity is a very weak force. But we'll see why it ends up winning over all the other forces. But it is very weak. Now look at this unit. Brr. Meters cubed over kilograms seconds squared. Who came up with that? Well, let's talk about that. So G is this multiplication factor. This is not how it's actually determined. So Cavendish found a way of measuring this, and it's pretty complicated, pretty cool, but I don't want to get into it right here. But basically, think of it this way. If I took 1 kilogram of matter and placed it its center 1 meter away from another kilogram of matter, and I could somehow measure the gravitational force of attraction between them, it would be 6.67 times 10 to the negative 11 newtons. Okay? That's not actually how it's measured. It's kind of tricky to do because that's too small to measure. You had to use bigger masses. But anyway, people figured out, and as soon as they did, they applied the gravitational equation to figure out the mass of the world. Pretty cool, huh? But here's what we come up with: 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. Let's dive in on that. What is up with this funky unit here? You're never going to have to explain this on the AP test, but let's just talk about it because it is kind of interesting. Remember, I want to be able to express force in newtons. So I want to take this equation here and say, okay, I'm going to express force in newtons. Now, if you remember, 1 newton is equal to MA. So kilograms per meters per second squared, kilogram meters per second squared. So I multiply kilograms times acceleration, kilogram meters per second squared is going to equal G times, well, if I multiply kilograms times kilograms, I get kilograms squared. I'm going to measure distance in meters, so I have meters squared. So the thing is, I need to find something that I'm going to multiply here, that when I multiply these units, I get these units. And so this is why this works. I have meters cubed here, and I have meters squared here, so I'm just left with meters in the numerator. I have kilograms squared here, and I have kilograms here, so I'm left with 1 kilogram up above. And I don't have any seconds squared at all, so I had to have a second squared here. And that ends up reporting out to me in newtons. So that's why it's that way. Now, let's move on. Most of my students get really confused between mass and weight, and it's really important that you're not one of them. Okay, I know that your doctor says you weigh 55 kilograms. Well, your doctor's not telling the truth. Your mass is 55 kilograms. You have 55 kilograms of atomic particles in your body. that are being pulled down towards the center of the Earth with a gravitational force, which we would measure in newtons. So please remember, m is mass, mg is the force of gravitation. And the thing is, if you were to go to the moon, let's say you weighed 60, let's say you had 60 kilograms of mass. On Earth, you'd weigh 600 newtons. But on the moon, you'd weigh 1/6 of that because gravity is 6 times weaker there. So you'd only weigh 100 newtons instead of 600 newtons. But your mass would still be 60 kilograms. You didn't lose any atoms by going to the moon. You lost gravitational force by being near an object that had a lot less mass than the Earth does. So let's just try looking at some of the proportional reasoning questions that College Board likes to ask. And they're good at trying to unpack gravity here, okay? So let's say I have a person who weighs 800 newtons on Earth. How much would they weigh on a planet that had half the mass of Earth but the same radius? Well, I look at this equation here and I see the force of gravity is directly proportional to mass. So if I have half the mass, I'm going to have half the force of gravity. Half of 800 is 400. That's how much you would weigh on that planet. Well, let's do the same thing, but this time we're going to say the planet has the same mass, but it has half the radius, so it's considerably more dense. Well, I'd say, all right, well, the force of gravity is proportional to 1 over the radius squared. And since the radius has now been reduced to half of what it was, 1 over 1/2 squared is the same thing as saying 4. So I have 4 times as much gravitational attraction. So instead of it being 800 newtons of weight, I would have 3,200 newtons of weight. Yikes. Now let's try changing both things. And College Board really likes to do this. They often ask questions where we have to change 2 aspects of gravitation, but it's not a big deal. Okay, so you weigh 800 newtons on Earth. How much you weigh on a planet with twice the mass of Earth and a third the radius? So I say, well, the force of gravity is proportional to m over r squared. And we haven't really done that much this year, but it's not that big a deal. So I just say, well, okay, so I have two mass has gone to 2m, radius has gone to 1/3 r. So 1/3 square is 9. So I have 2 over 1/9. That's the same thing as 18. So 18 times 800. Whoa, on that planet, I'd weigh 1,400, 400 newtons. Wow. Okay, let's talk about gravitational fields. So fields are going to be really important if you take AP Physics 2, but we're going to touch on just a little bit here in AP Physics 1. So a force field is basically, think of it as force vectors that point towards the larger mass. So this field, this force field extends an infinite distance away from any given object. Let's consider the object to be the Earth, okay? So Earth's gravitational force field extends infinitely far away. Uh, and think of it as a bunch of vectors that all point towards the Earth. Now, I know this looks like an explosion, but really, if you notice, these are just arrows pointing towards the Earth. Okay, and so the idea is then that if you move away from the Earth, you can see these lines are getting farther apart from each other. And if you think about a three-dimensional surface, then the density of those lines is going down as a function of the square of the change in distance, right? So if you get 2 times farther away, these vector lines get 4 times farther apart, right? So if we then take a test mass, a small mass, and I put it in that vector field, then I can figure out what's called the gravitational field strength. So the gravitational field strength is basically the force per unit of mass. How many newtons per kilogram of force is going to be exerted on that test mass at a given point in this gravitational vector field? I know that sounds scary, but really you're going to see it's pretty straightforward. Right now, those words sound like, yeah, what is gravitational vector field? But think about it. Here's your first hint. We're going to designate gravitational field strength with a letter G. Now, I've been using intentionally the term gravitational field strength instead of G or acceleration of gravity because it's just a better term to use. But here you go. If we're near the Earth's surface, the gravitational field strength is 10 meters per second squared. Because if you take newtons and divide it by kilograms, you get meters per second squared. But if I double my distance from the center of the Earth, the gravitational vector field gets more spread out. And so if I'm twice as far away, I have 1/4 the gravitational field strength. So now there'd just be 2.5 newtons per kilogram. Or in other words, it would accelerate at 2.5 meters per second squared instead of 10. So you can think of this just as the rate at which the test mass is going to accelerate at whatever part of the vector field it happens to be in with respect to the larger mass. How do we calculate this gravitational field strength? Pretty cool, actually, and not hard at all. So we say, look, we've got to get familiar with this equation. This is a good one to know. So gravitational force is equal to gravitational constant, m over r squared. Now, gravitational force is also defined as, how hard we've always been saying all year long, what's the weight of this book? What is this normal force? We said, well, it's just mg, right? So the gravitational force is mg, but it's also equal to this. Now, this is the little m. This is the test mass. The book on the table, that's the little mass. The Earth is the big mass over here. So the little mass cancels out. And I'm just left with G is equal, little g, gravitational field strength, is equal to the gravitational constant times the mass of the larger object, the planet, divided by the square of the distance. So this is a good thing for you to have just knowledge of, that the gravitational field strength is just G times m over r squared. So it's just basically it's this equation, but we're taking out the little m. So let's just try this here. So I have an ant in outer space, 2 meters away from the center mass of a 100 kilogram object, astronaut. How fast will it accelerate towards the astronaut? Sounds hard, but it's really not, because all I have to do is this. I say, okay, well, the gravitational field strength is defined to be Gm over r squared. Now, I assume the astronaut is more massive than the ant, so the astronaut's mass will go here. So that's 100 kilogram there. The distance between their centers is 2 meters, so that's uh, uh, r here is going to be 2 meters. 2 meters squared, that's 4. So 100 divided by 4, that's 25. Oh, wow, that's pretty fast to excite. Not so fast. Don't forget, we have the gravitational constant here, which is 6.67 times 10 to the negative 11th times 25. So it's going to be significantly slower than that. What we find is, oh, my face is in the way, that it's going to accelerate at a whopping 1.67 times 10 to the negative 9 meters per second squared, but it is going to accelerate. All right, let's go to the next one here then. Oh, that's the end of this. We're done. Congratulations. You've learned about gravity. We'll have a lot more to say about it in future ones. See you later.